Okay, we will go ahead and get started so we can get on with today's program. We are really excited to have Surya Selvam here today. Surya is a student at J.R. Tucker, and he's here to talk a little bit about machine learning and specifically how it applies to a project that he did earlier in the year. So hopefully we'll hear some fundamentals and some basics about what he applied into the project, and then we will dive further into the case study and hear about his specific project. So Surya, thanks for joining us today. We're excited to have you. You are officially our first student presenter on the platform, but hopefully not the last. So I will turn it over to you, and good luck. Thanks so much for joining.
Yeah. Thank you for that introduction, Mr. Surface. Good afternoon, everyone, and welcome to my presentation on machine learning. Today, I'm going to be talking to you all about how I use machine learning in my climate change analysis in order to make some better predictions on climate change trends. So before we start, I'd like to say in no way am I an expert, a savvy in this field. It's been my passion that's driven me forward in order to deliver and share this presentation with you all today. So without further ado, let's get started. Okay, so what is machine learning? I know that many of you may have seen it in the movies or may have heard it in the news recently. In fact, it is one of the biggest, most growing trends in the technology revolution today. But what exactly is machine learning? So machine learning in simple terms is essentially enabling computers to learn something, whether it's what a car looks like or what Amazon stock prices look like over time, through simple data patterns without being explicitly programmed. So that might seem a little daunting, so let's break it down with a really simple diagram right here. For a second, I want you to put yourself in the shoes of this guy over here, the computer. In order to do that, let's go back to when we were once children. So I remember when I was a child, I used to play with the leapfrog toy a lot and used to memorize flashcards from my elementary school. And that's all about what learning is, right? It's about memorizing information over time, running through information and getting familiar with it. In fact, believe it or not, that's how the machine learns as well. Computers learn by looking over data, repeating the data over and over again until it becomes familiar with what it's looking at. So let's look at the diagram over here. Let's say that we want to make our computer learn what a car looks like and be able to predict whether it's a car or not a car if it's given a new image of a car. The way we do that is give it thousands of images of cars from around the world. Give it thousands of those images and input into the model so that the model can look at every single image, look for any features that are common among them. But like any good teacher, data scientists have to make that lesson easy for the computer. So we don't want this little computer to have such a hard time looking at all of these data sets and then becoming overwhelmed by it. So data scientists are going to add this little step over here called feature extraction to let the computer know what it's looking at. So let's talk about the car example over here. Let's say we want our computer to learn what a car looks like. We're going to feed in tens of thousands of images of cars around the world. And then what we're going to do is feed it some features to look out for. That's called feature extraction, where we're going to feed in features like the rear view mirror, the windshield, the headlights, the tires. These are some features that are unique to cars. And we're going to feed it into the model, let it know that when you're looking at all these images, look out for that feature. For the example of the Amazon stock prices, all of this data is really complicated and overwhelming for the model. So we're going to give it a nice, easy approximation of the data that best approximates it without being too complicated. We can feed that feature into the model. So to recap, machine learning is all about really allowing the model to learn from so many iterations, so many repetitions, looking at the data each time. And when we feed those features in, by that time, the model should have a good idea of what it's looking at, that all those pictures are cars. And when it's given new data, it can predict whether it's a car or not a car. And here's where the fancy of machine learning comes into play. Let's say that our model makes the wrong prediction. It looks at a car, but it says it's not a car. The machine can then go back into the model, adjust itself a little bit, and then adjust itself, keep adjusting itself in an iterative method until it gets the prediction correct. That's where the learning element of machine learning comes into play. So in order to understand machine learning, we're going to have to understand three classes or disciplines of machine learning that are initiated depending on the circumstances we're learning in. So the first one is supervised learning. This is the one that was predominantly used in my case study. So supervised learning is when we are training a model and we already have existing data to train it on. This is especially used when we're looking at stock prices. Let's say we want to predict 2020 stock prices for Amazon. And we already have the past 5 years of data, right? We can use those past 5 years of data in order to train the model, make the model look at all that data, be familiar with it, kind of understand the direction maybe of where the stock prices are going, which is up, right? And then make predictions for the 6th year, which is 2020. So supervised learning is like that robust model. It's a very strong model. It's based on evidence that's already given to the model. So some examples of supervised learning is regression learning, where we already have data points already given to the model, and the model would look at these data points and try to fit a model through them that would best approximate it. Another example is image classification right here with this classic example. So here's a classic example of classifying two classic characters from two classic franchises. Dobby from the Harry Potter series and Gollum from the Lord of the Rings series. Let's say we want to make our computer classify between these two characters when it's given an image. What we're going to do is give the computer several images, thousands of images of Dobby from throughout the scenes in the Harry Potter series. Then we're going to do the same thing for Gollum. And by that time, the computer should be familiar with what Dobby looks like and what Gollum looks like, so that when we feed a new image of either Dobby or Gollum, it can classify either or. Supervised learning in the real world could be used in the medical industry in order to classify different types of diseases when it's given pictures of those diseases. So it's really used when already defined evidence is present. And then for number two, unsupervised learning. Unsupervised learning is used in order to look at differences between data. So here is a good diagram that kind of sums it all up. In unsupervised learning, we have like this data set, for example, we have so many different clusters of data. And what the machine learning model is doing is looking at how these clusters might be different. So for example, just by looking at the data, we can see that these data points are kind of situated around each other, kind of grouped together, and they have so much distance from this cluster over here, right? So they're kind of different from each other. So the machine learning model looks at that and says, okay, these clusters are kind of grouped into one group. These are grouped into, another group, and it can separate between the two, or between the three here. So in the real world, unsupervised learning would be used for cybersecurity in order to detect hackers and breaches in servers, and for fraud detection. So an example of that would be in the real world when we're searching up something on Google. When someone searches something up on Google, we are accessing data legally from a server, right? But let's say one day there's a hacker and he wants to illegally take data from, he or she wants to take illegally from the server by maybe inserting something, say a virus. So the machine learning algorithm says to itself is that in the real world, people search something up and legally take or access data from the server. But in this case, a different behavior has happened where the person is inserting something. That is different. That's an anomaly, right? It's different from the normal. So that must be something like hacking. And fraud detection, it might look at a behavior and say this person is making a transaction the wrong time of the day, or to a really weird service or company, and say this is different from what most people do. So that must be fraud. And number three, we have reinforcement learning, probably the coolest guy on the block. Reinforcement learning is probably the machine learning equivalent of learning from experience. So here we have an example. We have this robot named Charlie over here, and he wants to get this gift. okay? But in order to get that gift, he has to circumnavigate a series of obstacles. So he's going to use reinforcement learning, which is essentially a reward-based learning. Every time he goes in the wrong path towards the obstacle, it's going to register as a failure. But every time he goes in the right direction, okay, which is up here, it's going to register as a reward. And he's going to keep doing that until he makes the moves to get to the gift. And then if we place Charlie back here after doing it, he can recite all those steps again and get to the gift almost immediately. So a good example of that in the real world is advertisements. You might get on Google, you might see those recommendations. You're like, wow, how did Google read my mind and give me an advertisement that I'm interested in? Well, it's all about reinforcement learning. Let's say that you are interested in Disney Plus, you love Disney movies, and you get an advertisement from Disney Plus, and you click on that advertisement. The machine learning algorithm says to itself, okay, the person clicked on the Disney Plus advertisement, so he might like TV streaming services. So it's going to give this person another advertisement from another TV streaming service. And an example of that would be Apple TV. But let's say you don't like Apple TV and you don't click on that advertisement. The machine learning model would tell itself, okay, this person likes TV streaming services, but maybe not the path of Apple TV. So let's go through another path, maybe another TV streaming service or more Disney Plus content. So that's how reinforcement learning is like a decision maker and learns from its own experience. So here are several types of algorithms in order to initiate these three classes of machine learning. So the first one over here, I'm just going to go over them really briefly, is linear regression, that classic y is equal to mx plus b. Linear regression is a type of supervised learning, and it's because we already have existing data points. We're training the model using those data points, and we're fitting the best approximate regression that can fit all the data points. And then we're going to come over here to logistic regression. This is a modification of linear regression, and this is where data is between two extremes, between 0 and 1 most of the times. And it's used for a lot of probability applications where as x increases or decreases, our y is going to be either 100 or 0% or somewhere in the middle. And then neural networks. This is where machine learning comes that advanced stage. So neural networks are used in order to look at the correlation between our input variables. We could have several input variables, one or many, and the correlation between these input variables and the output variable. It's going to do that through something called a hidden layer. So in this example right here, we have 3 input variables. Those input variables are going to go through the hidden layer, which is going to convert them into output layer. It's going to do this, okay, iteratively over time. And let's say our predictions are not close to our actual output. Then it's going to go back into the hidden layer. It's going to adjust those weights and biases, those coefficients that convert our input into output. It's going to adjust them a little bit so that over time, our model becomes specialized in taking these input layers and making the best prediction that's approximately the same value as our output layers, as our output variable. So in that way, our neural network is a supervised learning model. Now over here, we're going to get to decision trees. This is a classic reinforcement learning where our model is going to make one decision, and that doesn't work. It'll go through another path. And then we have support vector machine here. Support vector machine can be used in unsupervised learning in order to create a regression that can split 2 clusters of data. And it can also be used in supervised learning, where it can guide the best approximate regression through data in order to create a regression that approximates the data as best as it can. And last but not least, we have ensemble models, which are basically a combination of different models. They're a combination of decision trees and support vector machines. And the way it works is very similar to a neural network. We start with a weak learner, usually a straight line. Let's come up. And then when we have that straight line, it will adjust its model a little bit so that it gets as close as it can to the data points here. Okay, so now on to my case study. So I want to talk a little bit about why I decided to focus on climate change today. So why did I decide to study climate change in this case study? Well, first of all, I'm a climate change activist, and for many years, I've wondered why people don't really understand why climate change is. I really wanted to understand why people don't understand why climate change is so severe. Because the reason why is because climate change is so complicated today, right? It happens, right? It's happening and occurring as we speak. And it doesn't register as an imminent threat to the human mind. So what I wanted to do is I wanted to act the role of a data scientist. I wanted to take this really complicated real world situation, so complicated as climate change, and convert it into numerical values, kind of represent it as numerical values that can actually tell us how big or how small the situation is. So while I was doing my research, I came across some important stuff. So the first one was a research paper by Dr. James Hansen of Columbia University. And I'd read this research paper about how greenhouse gases like CO2 and methane, how they, because of their molecular movement in the atmosphere, how they force kinetic energy down into the lower atmosphere where we live, right? And keep it within the lower atmosphere. And I read a little bit about that. And I read another research paper by another professor named Dr. Kerry Emanuel of MIT University. And he had attributed these greenhouse gas emissions to the increase in tropical cyclones. And I was really interested by this, interested by how CO2 can actually influence the intensity of tropical cyclones over time. So I decided to use machine learning in order to look at this relationship and see how one trend can influence the other. So here's a little bit of background on my study. This right here is a diagram by Dr. Kerry Emanuel, and it is the diagram that explains how CO2 in the atmosphere right here influences tropical cyclones. So it's called the Carnot cycle. Essentially what happens is when there is entropy in the atmosphere, when there's molecular movement between CO2 gas molecules in the atmosphere, heat is forced down into the atmosphere. So these arrows show that heat being forced down to the atmosphere, and it's forced all the way down to the sea surface, which is the ocean surface, moves across the ocean surface, and is cycled back up. What that does is that creates wind speeds, winds down at the ocean surface, and develops a storm wall, which becomes the tropical cyclone. So I was really fascinated by this. And what I did is I boiled all of this real world situation down into a study where I took atmospheric entropy of CO2 and looked at how that influenced the radiative forcing of heat down into the surface, and looked at how that in turn influenced the net heat flux of ocean into the surface, which is this stage right here, A, and how all three of these variables together influence the cyclone potential intensity, which is a measure of how strong cyclones are. And I did this all through a neural network where I have 3 input variables. So I'm trying to get this one input variable, this one output variable. Okay, so why use machine learning? Well, first of all, climate change is really complicated. It's a real world situation that has so much oscillation when we actually look at it in a graphical presentation. So this is accumulated cyclone energy index. It is an index that measures the intensity of hurricanes. And as you can see, a lot of this data is really messy. There's a lot of ups and downs in it, or oscillations. So we're seeing a lot of outliers up here and down here, and so many ups and downs, and it's really hard for us to really understand that data. So simple regressions aren't going to work on this. They're not going to get the best approximation, and not going to predict what it's going to look like in the future. So what we can use are these advanced machine learning models like gradient boosting, which is an example of an ensemble model, and neural networks, in order to really track this regression section by section, in order to decide what regression to use for each section, so that we can make the best overall approximation of this data set. Okay, so here is my method and the evolution of the project. So right here in this diagram, this is kind of the step-by-step, the steps I took in order to kind of complete my project. So the first step is the data preparation phase, where I had 4 data sets here: CO2 concentrations, sea surface temperatures around the equator, accumulated cyclone energy index, a data set for that, which we just saw, and radiative forcing right here, which is the amount of heat coming down to the atmosphere. I had these 4 data sets, and because these data sets, like we saw before, are really complicated with so many oscillations, I needed to prepare these data sets by smoothing the data sets and looking for some simple features. And I used something called a spline or piecewise function. We'll look at that later. And I also statistically downscaled the data using 2 techniques called moving average and low S technique. We'll look at that later as well. And then from step 1, I went to step 2. I acknowledged that a lot of these data sets don't have the same time frame. I wanted to look at from 1820 to 2019 how these variables here were increasing. So a lot of these data sets didn't have the same time frame, so I needed to predict a little bit, kind of like extrapolate a little bit. Like some data, for example, sea surface temperature was from 1880 to 2011. I needed to predict from 1820 to 1880, and also from 2011 to 2019. So a lot of different prediction going on there. And what I use is supervised regression learning, where I took the already existing data, trained on that, and tried to predict outward. So here's an example of my code. Here, I'm going to go to this. Here, I'm going to reconnect really quickly. And this is an example of one variable. It's ACE right here, accumulated cyclone energy index. And all these oscillations here, I wanted to kind of, this is a little overwhelming for the model. So the first thing to do is prepare the data. So preparation is going to look like this, where the first step is to smooth the data using something called a piecewise function approximation. And I called this function right here called piecewise smoothing. Put in 3 parameters, so 2 x parameters, which is the years since 1850 or 1880, and the years since and the time since 1880. And then I had my y variable, which is ACE, the accumulated cyclone energy index. And what comes out, the output looks like this. So we have all of our data here, and we're basically getting smoothing. Okay, we're smoothing the outliers out. And if we zoom in, it looks like this, where we have our outliers, which are the red here, the red dots, the red points. And here is the smoothed regression that goes through it. The reason why I did this is because normally in data science, data scientists will eliminate these outliers, not even look at them. But because outliers are happening so frequently, they must be really important. So I decided to kind of give a little bit of definition to these outliers, kind of really understand the general direction of these outliers and what it looks like on a smoothed level. And then I went through some data downscaling. So that's the next step in our data preparation phase, where I used 2 different moving average techniques, simple moving average and exponential moving average. These are used in a lot of stock price evaluation applications. And so I used these 2 techniques, had a function for each one right here. And then I also used another technique called locally weighted scatter plot smoothing. That's low S, and had the function right here for that, passing in my 2 parameters. And that is going to look like this right here, where purple is the exponentially smoothed or exponential moving average. I'm sorry about that. And the cyan blue right here is the simple moving average. The red is just a combination of the 2. And the dark blue here is the low S, just gives us the general direction of the data. And when we combine all three of these techniques, we get this yellow line here, which is the final downscale data. And now it's time to get our supervised regression learning done. So right here, we are going to define our machine learning model, and I'm going to call it ACE boosting model because it's a gradient boosting model. So I call it the ACE boosting model. And I'm going to call a class called machine learning algorithm here. I'm going to pass in my X values like before, which is here. And then I'm going to pass in the Y value, which is the moving average, this yellow line right here. And then we're going to pass those values in, and we're going to call this technique called test split valid. And what that does is it splits our data sets into train and test points. So in the red, we have our train data points. In the blue, we have our test points. And the reason why I'm doing that is because I want to train the model on the red points first, kind of fit the red points and train it on the red points, then try to predict for the blue points and see if it's good enough, if it has good accuracy. Okay, and then we have our training phase here. So in the training phase, it seems like our model is on the point. It's on the spot. It nailed it. All the predictions are really good. So yellow is the predictions, and I don't know if you can see it, but the green dots are the actual data points. And it came up with a mean absolute error of about 0.0026, which is basically zero error. So the prediction is really good. But there's only one problem. This is on the training data, which is the red points. What about the test data? And this is where the model isn't so good. When it's given new data, it makes some really wildly inaccurate predictions here. And the reason why is because something called overfitting, where the model gets too cozy, too comfortable with the training data points here in red, that when it comes to the test data points, it doesn't do so well anymore. It gets too overconfident with this stuff, with this data, that with the test data, it's very inaccurate. So what I did is I wrote a simple function that would look at all the iterations of the model and would look at which is the best one that has the least amount of error. And it seemed that 500 max leaf nodes was the least amount of error. That was the iteration that had the least amount of error. So that's the model that I used. And when we set our model to 500 max leaf nodes, we're going to get this as our predictions. So these predictions are much better than before. It's not too good, it's not too bad, where it actually tracks the data as best as it can. And once we have this, it's time to actually predict. So I developed this extrapolation set from 1820 to 2020. And here I made some predictions from 1820 to 2020. This is what it looks like. So after the data preparation and supervised regression learning were finished, step 3 was all about creating new data sets. So this I won't go over too much because this involved a lot of different formulas, a lot of complicated integration formulas that took in like 2 data sets, for example, CO2 concentration and sea surface temperature, and calculated another data set. So once we finished all that up, and this is represented by the blue lines, we get 3 or 6 variables really. So we have 3 independent variables, which are input variables: atmospheric entropy, sea surface net heat flux, and radiative forcing. And we have 3 output variables, which are dependent variables. And in this study, I didn't really look at these 2 variables. I looked mostly on this variable, which is potential intensity. And what I did is I fed these variables into a neural network in order to train them, in order to look at how these input variables were correlated with the output variable. And then the reason why I have this double arrow is because once we train it, we're going to put these input variables back into the model. And then we're going to predict and see if it was close to the actual output data points. So that is step 3. Step 4. There's a little bit of typo there in the presentation. And that's the neural network stage. So the neural network stage looks like this. So here we have three variables, our entropy, right? We have our three variables, entropy, sea surface temperature, and net heat flux. And we want to look at how these variables are correlated with each other. So we're kind of seeing a similar trend between each other, right? They're both kind of exponential in growth. And then we're going to see how these three variables contribute to our potential intensity right here. Okay. And this is a little bit of feature extraction going on here. And this is where we actually build the model. So this is a very simple layout, a map of how the model should look like, where we have our input layer right here that takes in our inputs, our X values. And then we have 4 hidden layers with weights and biases to convert the input layer into the output layer. And here's the output layer. And then here's the center of attention. So this is where I fit the model with the 3 X variables we have, the 3 X data sets. That's entropy, sea surface temperature, and net heat flux. And then I fit it with Y, which is the potential intensity. And I set a number of epochs. So epochs are just essentially the number of iterations of the data set. So in this case, it's iterating 1,000 times, learning 1,000 times just to see how X is correlated with Y. And then we have this little attribute here called validation split. And what it does is just splits the data into training data set and test data set. So here we have our 1,000 iterations, or epochs. At epoch 0, which is iteration 1, we have a mean absolute error of 1,600, about 2,000. That's really bad. That means that our model is basically a dumb model. It's a weak learner right now. And it didn't do so good predicting. Then over time, about 100 epochs, the model gets better. It drastically decreases its error to about 100 mean absolute error. So because of that drastic decrease, we can kind of assume that the model has gotten better in predicting and fitting those values, the X and the Y. And then after 200 iterations, we get 100, which is the lowest. And after that, it starts to increase over time. So what the model says is, okay, at epoch 200, this is where the model was the best. This is where it was the most accurate. So we're going to use this model at epoch 200. This is what it looks like, the error. It decreases drastically, then increases. We're going to use it. We're going to use this model right here between 200 and 400 epochs. And then here is where the neural network is finally finished. Okay, so we actually predict our X values here. We fit it one more time. We predict our X values one more time. And then we show the predictions versus the actual values. So in red, we have our actual values, our actual potential intensity values that we calculated in step 3. And in blue, we have our predictions for potential intensity. And we can see that the predictions are pretty good, has relatively low error, but there are some small issues. For example, when our actual data points kind of have a small dip, our neural network predictions kind of react a little too heavily here. But all in all, it's a pretty good prediction. And when we're given new CO2 data, new net heat flux data, and new sea surface temperature data for 2020, this model can predict that. It can predict what the potential intensities for the hurricanes that summer would be like. Okay, so that is my study. And really quickly, I'm going to talk about the building blocks you can, the steps that you can take in order to learn machine learning or improve your game for machine learning. So step 1, the language. There are 2 important data science languages that you can learn. So Python and R are the most common languages. Python is definitely the most famous one that's really growing and getting a lot of popularity among data scientists. I use Python for my study. And in step 2, after you learn your language, it's time to get familiar with some data analysis libraries. This is where feature extraction comes into play, where you can learn some of those data analysis libraries to kind of look at some of the features in your data sets. So the four libraries that I use were pandas, NumPy, Matplotlib, and SciPy. So pandas is that library that allows you to take a data set and look at it in a table manner. So it's a table format. And then NumPy allows you to kind of get some statistical measures, look at the standard deviation of the data, the amount of variance in the data set. And then Matplotlib allows you to visualize the data in a graphical projection, kind of put in a graph format, with that X and that Y axis. And then SciPy is my favorite. This is the one that allows you to interpolate missing values in a data set. It allows you to smooth the data set out using the piecewise the piecewise approximation function. And it also allows you to downscale the data. So it helps you with that step 1 and that step 2 for my study. And then step 3 in your machine learning journey, it's all about learning the primary machine learning toolkits. So the two that I used were scikit-learn and TensorFlow by Google. And the primary machine learning toolkits essentially give you a foundation, a basic algorithm that you can use in your machine learning program. So I used support vector learning, and I used the gradient boosting ensemble model from scikit-learn. And I kind of built on top of it a little bit to customize for my study. And then I used the neural network given by TensorFlow and built on top of that as well. But you can also use Theano by the University of Montreal. Theano is very similar to TensorFlow because it does give some basic neural network models. And you can also use the Prophet by Facebook. So Prophet is a little bit more of a specialized library that allows you to do time forecasting. Let's say you have stock prices and you want to predict future stock prices. It allows you to kind of look at and create the best regression to make future predictions. So I use gradient boosting for my time forecasting, but Prophet is equally as good. And then step 4, after you finish up learning those primary machine learning toolkits, you can learn some additional machine learning frameworks, ones that are a little bit more advanced. So the most common one is Keras. This is the one that I used for my neural network. Keras allows you to expand the power of deep learning, they expand the power of neural networks, and it allows you to increase the amount of hidden layers, increase the amount of neurons in those hidden layers, those weights and biases in those hidden layers. It allows you to increase the power and the scope of your neural network models. And this Keras, it can be implemented on top of TensorFlow. But PyTorch and Caffe are also two other libraries that you can use. I've never really worked with them before, but pretty sure they're good. And then step 5, this is not really a step, but this is something that you can use in case you want to kind of learn a little bit more about machine learning, maybe look at some other projects that other people have completed. So the first one is Kaggle. This is a good online resource if you want to learn and you want to get some hands-on experience. So they have courses from beginner to advanced, and they also have competitions where you can actually compete against other machine learning students at your level. So they would actually give you data sets and they would tell you to kind of use different machine learning algorithms to make approximations and predictions. And towards data science is a data science blog where machine learning experts could post their projects. And if you're beginning to learn machine learning, you could go on it towards data science and you could search up some projects and get some inspiration. So what does machine learning look like in the future? Well, for climate change analysis, we're going to start using it a lot more in order to predict climate change trends. But machine learning is definitely going to increase its role in the future. It's going to start taking up so many different things in our daily lives. So the biggest use case of machine learning are virtual assistants, the Google Home and the Alexa, right? This is something that's definitely improving and growing over the years. And then another one is finance in the finance industry, in order to predict stock prices over time, or maybe even predict how the financial portfolio will go and how much money some investor would make in the future. machine learning would be used in that case. And then for self-driving cars, Tesla is using machine learning in their cars in order to make smart cars, and other car companies are also using them. And also in personal commercial products. So the Apple Watch is starting to use machine learning in order to track a user's fitness over time and predict how their well-being and how their health will be in the future. And another thing is public services / government services. Machine learning will definitely start being used for government services in order to create smart grids, in order to learn how users are using electricity and consuming power, so that we can kind of limit our power consumption and help climate change, help avoid climate change through the years. So smart grids is another use case of machine learning. So that finishes up my presentation.